Have you ever bought a bag of rice or weighed yourself on a digital scale? Whether you're measuring grocery weight or performing lab experiments, you're likely using kilograms. That's because the kilogram, abbreviated as kg, is the official SI unit of mass. Back in 1889, 1 kilogram was defined by the mass of a platinum iridium cylinder stored under controlled conditions at the International Bureau of Weights and Measures in France. Interestingly, a liter of water at 4 degrees Celsius also weighs approximately 1 kilogram, a practical standard often used in science labs. Over time, the kilogram became the cornerstone for measuring mass in everything from household items to chemical compounds. But not everything we weigh comes in kilograms. When it comes to powders, solutions, and lab samples, we often need to measure much smaller masses. That's where grams and milligrams come in. A gram, symbol G, is 1,000th of a kilogram, that is, 1 gram equals 0.001 kilograms or 10 raised to the power minus 3 kilograms. And a milligram, symbol mg, is 1,000th of a gram or 1 millionth of a kilogram, written as 10 to the power minus 6 kilograms. Milligrams are especially useful in medical dosages and fine chemical preparations where precision is critical. For instance, an aspirin tablet may contain just 300 milligrams of active ingredient, a tiny amount, but accurately measured thanks to these smaller units. On the flip side, when we are dealing with agricultural produce or industrial materials, kilograms can feel too small. That's why we use quintals and metric tons for large-scale mass. A quintal is equal to 100 kilograms, a common unit used in grain markets and warehouse. Even bigger is the metric ton, which equals 1,000 kilograms or 10 quintals. Imagine transporting steel beams or exporting wheat. Here, tons give us a practical, scalable way to report and compute weight. On screen, you see a visual comparing a 1 kilogram weight to a 100 kilogram quintal and a 1000 kilogram ton, a simple way to grasp how these units build up. Now let's shrink things down all the way to atoms. In the world of chemistry, we often talk about the mass of particles that are way too small to measure in grams or kilograms. That's why we use the atomic mass unit, abbreviated as AMU or U. It is defined as 1/12th of the mass of a single carbon-12 atom. In kilograms, that comes out to about 1.66 times 10 raised to the power minus 27 kilograms. It's a tiny but incredibly important unit because it allows us to express the mass of atoms and molecules in a meaningful way. For example, the combined mass of 6.02 times 10 raised to the power 26 carbon-12 atoms is exactly 12 kilograms. That's the beauty of atomic mass, it bridges the atomic and the measurable worlds. So how do we move between these micro and macro worlds? The answer lies in Avogadro's number, 6.02 times 10 to the power 23, which tells us how many particles are in 1 mole of a substance. This number connects the atomic scale with everyday lab scale quantities. For instance, 1 mole of carbon-12 atoms, that's 6.02 times 10 to the power 23 atoms, weighs exactly 12 grams. That's how chemists translate molecular mass in atomic units into grams or kilograms on a balance. This concept is the foundation for stoichiometry, helping us relate the number of particles to actual quantities we can weigh and mix in the lab. What if we go beyond atoms, way beyond, into the stars? Well, scientists have a unit for that too. It's called the solar mass and it's used to describe the mass of stars and galaxies. 1 solar mass is the mass of our Sun, approximately 2 times 10 to the power 30 kilograms. That's a number so large, we'd never use it in a lab, but it's essential for astronomers and astrochemists studying stellar fusion, planetary formation, and cosmic reactions. From the tiniest subatomic particle to the largest star, The unit of mass can scale across the entire universe, and all of it begins with the humble kilogram. Let's quickly recap. The kilogram is the standard unit of mass in the SI system. When dealing with small samples, we use gram and milligram, while large scale quantities call for quintals and tons. At the atomic scale, we rely on the atomic mass unit or U, defined as 1/12 the mass of a carbon 12 atom. And for cosmic masses, we scale all the way up to the solar mass, equal to 2 times 10 to the power 30 kilograms. In between, Avogadro's number helps us link particle counts with measurable weight. I hope this session helped you see how mass, though often taken for granted, is an essential part of every chemical equation, every dosage, every planetary model. In our next topic, we'll look at units of time and how every second counts in chemistry. Until then, stay curious and keep measuring the world one unit at a time.